Okay, so we're going to finish off the notes. We're going to start out with reaction mechanisms. Most reactions, we see them as the overall reaction, the reactants and the products. But in actuality, very few reactions just happen in one step. Most of them are multi-step. But we don't see that when we just see the balanced equation. So what a reaction mechanism is, showing you the mechanism that it happens. Okay, it's a series of steps. The intermediate is a species that is neither a product or reactant, but it shows up. So basically an intermediate is produced in one step, but then it's immediately used up in the next reaction of the reaction mechanism, okay? And so the way that we can recognize an intermediate is it's created and it's a product first, and then it's a reactant next, and they'll cancel each other out. That's why they don't appear in the overall reaction. The elementary step is a reaction whose rate law can be written from its molecularity, which is its balanced equation. So basically, if it's an elementary step reaction, it actually is just a one-step process. And we can actually write the rate law from that one-step process. If it is not a one-step process, then we cannot write the rate law from the balanced equation. But if it is, then all we do is literally, or we're going to write the concentration of the reactants raised to their coefficients if it's an elementary step. Okay, so it has to tell you this is an elementary step. If not, it probably isn't. Okay, molecularity is the number of species that must collide to produce that reaction. It's represented by the elementary step. Unimolecular means it's only one molecule. Okay, bimolecular is two, and a reaction step involving the collisions of two molecules, and then that rate law would always be second order if it's an elementary reaction. Okay. The rate determining step is always going to be your slowest step. Okay. So if you look at something and they've told you which is the slow step, then that makes your life easier because that's going to be what determines how fast you go. Okay. And then, of course, if it's an elementary reaction, it's going to agree with the balanced equation. So your rate law would agree. So like if you had, a to the second, then you would need to have 2a in the balanced equation. Okay? Reaction mechanisms must add up to the overall balanced equation. And then they also must agree with the rate law. And here I want you to insert experimentally determined rate law, or put it in parentheses. Okay, because most rate laws are determined experimentally. So you either have had to figure out what the rate law is from data, or they gave it to you. Unless it's an elementary step. If it's just an elementary reaction, then it's going to be the balanced equation. Okay? Any questions so far? Okay. We can't prove mechanisms absolutely. We can only come up with possible probabilities. Okay, so here is a video if you want to go watch it later. It's called the clock reaction. There's actually a pivot lab that does the clock reaction. I haven't decided if I'm going to do that one or a rate law, because this weekend, Friday and this weekend, you're going to do another pivot lab. Okay, which I should probably grade the last pivot lab. I completely forgot that I needed to grade that until I just said that. I thought I was all caught up on grading. No, I'm not. I got to grade a limiting reactant paper. Okay, that's what Aish can do in class today, is grade the limiting reactant when she's my lab manager. Okay, so this is an elementary reaction here, okay, which means it's a one-stepper. This means we don't have to worry about experimentally determining that rate law. And so really and truly, all we're going to say is we would write it like this. And we would say rate is equal to K in O into O, because it is it's an elementary reaction. Okay, so we're not going to have to do anything. Okay, so remember, if we have an intermediate, it does not appear in the rate law. So we're going to see that here in a second. Okay. Oh, okay. So in this one, basically what you're going to do is you are going to, when you've got reaction mechanisms like this, you are going to take each rate law and you are going to add them to each other and then stop at the slowest step. Okay, so in this case, the slow step is first. It's the rate determining step, so we won't have to do anything but go past that. So we would write that as, oops, we're going to raise them to their coefficients. Oh, it's already in there. Rate is equal to K NO2 F2. Okay? The intermediates in this case would be F, right? That's the only intermediate. So we see that it matches our rate law, our balanced equation up here. Okay? So it matches our balanced equation for that, and we stopped. We didn't include the second thing. Okay? I want to give you an example of how you do that, because I don't think there's a good example. Let me look at what the next example is, because I think I remember, yeah, that's the difference between unimolecular, bimolecular, and termolecular. It kind of gives you the rate expression. But I want to give you an example of when the slow step is not first, and it's not one in there. So I'm just going to use A plus BC is going to yield up. Hold on. I got to come up with one. These aren't as easy to just make up on the sly. Let's see. So that's going to be my overall reaction, and here are my mechanisms. I'm not going to worry about charges. And we're going to say that this one is my slow step. And so we would say this is fast and this is slow. Can't spell slow. And I wrote too big. So this one's going to be fast, slow, and fast. So when I would be doing this by adding them up by the reaction mechanisms, I'm going to do did I put the last one as slow? Okay. Like I said, I'm making this up as I go, so I don't want to erase all strokes. So we'll do this one as fast. No, I want this one to be slow, otherwise this won't work.
You just had two slows, so.
Yeah. There. Slow, fast. Fast, slow, fast. I should probably make up one before I'm teaching in the middle of it, right? Okay. So the way that I would write this is I would write the rate is equal to K and then A, like that, right? And then I would write K is equal to B, and then I would stop. And then I'm going to add them up. So it would be rate is equal to K, A, B. Okay? So then it matches my equation, but it also is going with the experimentally determined. Okay? Or I determined it this way. Okay? Sometimes they might give you some reaction mechanisms, and they give you a rate law, and they say, hey, what's the slow step? And they're asking you to determine the slow step. So you have to do that sometimes as well. Okay? All right. I just wanted to show you where where slow wasn't the first step. The physical significance of the rate expression is the more molecules, the more collisions, so the faster the rate. Okay? So the faster the molecules are moving, the more likely they will collide, so then also the faster the rate. Okay? As an elementary step is a reaction whose the rate law can be written from its molecularity. This is not true of all of the overall reaction order. But if they tell you it's an elementary step, then you can get your rate law directly from the balanced equation. If it doesn't tell you it's an elementary step, then you can't. Okay? So here is an example of nitrogen oxide. And it says here's one possible mechanism. And then it just says what is the molecularity of this. And then show that sum in the net reaction. For some reason that shifted over. So the first thing we want to do is we want to take out any intermediates. So where do you see intermediates? N2O2, so we're going to cross those out. And then N2O. So we've crossed those out. So then we can write our overall reaction is 2NO plus 2H2 yields N2 plus H2O. And then the first step is we would write that rate.
Isn't it 2H2O?
It is. Forgot it. Forgot it on here too. That's why I copied. So then for the first one, we would write that as rate is equal to KNO. And that would be bimolecular. And then the second one is rate is equal to KH2. That's uni or unimolecular. And then the last one, hi Logan, just throw it away. I trust you. I haven't even taken attendance. Is H2. Also uni molecular. Because there's only one H2. That was supposed to have a 2 up here, I'm sorry. That's why it's bimolecular. I'm sorry, I forgot the 2. Because remember, when you're writing them from the reaction mechanism, you're writing them from the balanced equation for that step. But then you would add them all up, okay? We don't know which one our slow step is, so we can't actually continue this on. If it told us what our slow step is, then we would do that.
Why do you have 2 H2s instead of it just like H2s in a second?
Oh, because they're adding up. They're on the same side, so they add up. So remember when we did Hess's law for thermochem, and we added, when they're on opposite sides, we cancel them. We're on the same side, we add them together. So that process is still the exact same, okay? And the ones that are intermediates, we're crossing out, okay? If it is a catalyst will sometimes show up. Not very often, but sometimes show up. The way you know the difference between an intermediate and a catalyst, intermediate's going to be formed and then used up as a reactant in a subsequent step. A catalyst is going to start out as a reactant and then reappear as a product. Okay? Yes?
So you assume they're all fast unless they tell you?
Well, in this, notice I'm not adding it up to my overall rate law because I can't at this point. So if they had told us one was fast or slow, the purpose of this question was just seeing, can you write the rate law from each step, and can you recognize if it's uni or bi? So this wasn't asking us to determine the overall rate, and we can't do that without knowing which is the fast step. Okay. When you do it, it makes more sense. Like right now, it's kind of confusing, but when you sit down and do it, it'll start making sense with real examples. I need to put some more examples in the notes. Okay. That's why I made up that one, not very successfully, by the way. Okay, so the rate expressions are determined by experiment and must agree with the experimentally determined rate law. I don't know why I put a UMY in there.
It's a check mark.
Okay, it's a check mark on my notes. Check the slowest step is the rate determining step. The overall reaction is limited by and is exactly equal to the combined rates of all of the steps up to the slowest step. And of course, your reaction intermediates produced in one step, consumed in another. Catalysts will go in as a reactant and come out as a product. Okay. Sometimes catalysts will show up in your rate laws. Not very often, but they can. Your notes in a minute are going to say that they don't, and I need you to add in there they usually don't, but they can. I think I've seen it happen one time, though, in all my years. Okay. So this takes us to exercise 10. Again, they did the slow step first. So they're telling us what our rate law is, so this is what we want to match. So we want to match this. We want to make sure that when we're done, when it's all said and done, that we're going to match that. Okay? So it's going to be super easy since it's the first one. So slow step is going to be rate is equal to K, and then NO2, and F2. And then we stop because that's the slow step. Okay? we want to cross out any of our intermediates, which are just F. All right. And then it says, is this an acceptable mechanism? That is, does it satisfy the two requirements? Unknown. Okay. So, yes, it is an acceptable because it agrees with both the experimental rate law and the balanced equation. So it would be a yes. Okay. Also, it's bimolecular. Okay. Are we good so far? It makes more sense when you start working with it. I promise. Of course, increasing temperature, we've said this a couple of times about if you increase by 10 degrees, you basically double the reaction rate constant. So molecules must collide in order to react. Remember, only a small portion of our molecules are actually producing a product. Most of them don't have the energy required. And that's going to bring us to activation energy. We've been talking about activation energy. We've been saying to be successful collision, you have to have enough activation energy or overcome the activation energy to produce that reaction. And the rate of the reaction depends on EA. It's not a delta E, it's just what is the activation energy. Delta E has no effect on the rate. The higher the EA, the slower the reaction at a given temperature. Makes sense. Okay, if it's got a really high, it's going to require a higher temperature because it needs more energy. As temperatures increase, the collisions will have sufficient energy to overcome activation energy. Temperature will increase the amount of energy. Temperature has no effect on the proper orientation. Okay. As temperature doubles, the fraction of the effective collisions increases exponentially. Reaction rate is smaller than would be predicted for a number of collisions. This is because of molecular orientation. So just because they have enough energy, they still ain't lined up right, they ain't happening. Okay? Right? Okay, so this is your activation energy. Of course, at the top is where we have our transition state. So when we're labeling a graph, we've done this in the past, but now it's when we really, so you've seen it. The activation energy is the difference between the initial state and the top of the hump. Okay? The delta H, which is your enthalpy, is the difference between reactants and products. Okay? The only thing that goes to the top of the hump is activation energy. Okay? And it's from the initial state, so whatever your reactant is. Okay? So if we flipped that, and we had, that's what kind of reaction, by the way, endo or exo? Yeah, it's endothermic because the reactants are lower energy state than exo. If we flipped it and had an exothermic reaction, then your reactants are at a higher energy state. Your activation energy would actually be smaller from where it started to the hump. Okay. Several orientations. This is just a visual so you can see that, hey, unless they're oriented correctly, they ain't happening. Okay. So they have to be oriented correctly. This is something that is not on the AP formula chart, so you will not have to calculate the Arrhenius equation, but you should understand the theory behind it. Okay? So as the EA increases, meaning a higher activation energy, your rate constant is going to decrease. So the only thing that's really going to affect that rate constant of K is going to be temperature. Okay, it's going to be temperature. And so we're plotting this, natural log of K versus 1 over T for this reaction. And you can get the slope, and that'll give you what the activation energy is. But again, you're not going to have to calculate it, but you need to understand the theory behind it and why whenever I change my activation energy or temperature, why they affect each other and why they affect K. Well, that's really small. Okay? Where's the rest of that? Is it in your notes, the rest of that variation? It got left out of mine. I think that was the small one. Let's go back. Oh, it's just not lined up correctly, but it is on your notes, right? Okay. But again, calculation's not really there, but the theory is. You got to kind of have, it's kind of like Coulomb's law. You don't have to calculate it, but you got another theory behind it. Okay. Catalysts, such as enzymes in biological systems, increase the rate of a chemical reaction. How do they do that? Does anybody know?
Lower the activation.
They either lower the activation energy or they provide an alternate pathway. Okay, so the catalyst is something that speeds it up, produces a new pathway. It lowers the activation energy for both the forward and the reverse reactions. Some catalysts change the mechanism greatly, and some just change what the rate determining step is. Okay, so you've got to be able to draw this. Okay, so here is the main point when you're drawing a graph of a catalyzed reaction. Your energy of your reactants and your products is the same. We're not changing that. So therefore, it is also not going to be changing your delta E or your delta H. Okay? So if we had to do, like let's say it was an AP problem and they gave you this, but they're also asking you to calculate enthalpy and all that, your enthalpy would not change if it's catalyzed or not. It just will happen faster because it has a lower activation energy. So notice that delta E doesn't change, but EA comes down. But the main thing is draw a smaller hump and start your reactants and your products and end your products at the same exact place. Okay, don't draw a whole nother thing, just extend that. Okay, that's probably the number one mistake made on these graphs, that they go, oh, I just need to draw a smaller hump. No, you still got to start at the same and end at the same. Okay. Again, with effective collisions, the uncatalyzed. Okay, the size of your hump is not changing here because we didn't change temperature or anything. But look at what is changing. How much? Remember, that's that Maxwell-Boltzmann. I was trying to say. Never mind. I was going to flip those letters around. Okay, so the size of the hump hasn't changed, but where you have effective collisions, you have more of them now. Okay, because of that. So that's something else they may ask you to draw. Enzymes, of course, are biological catalysts. Homogeneous catalyst, of course, is present in the same phase as the reacting molecule. Usually we're talking about liquids. Heterogeneous or different usually involves gaseous reactants being absorbed on the surface of a solid catalyst. And either a new reaction intermediate is formed or the probability is, we sometimes call these surface catalysts. Very, very common in refining and petrochemical area, very common in that, or even just chemical. In most chemical plants, those big towers that they're using, they've got some sort of catalyst in there to speed up that reaction, because the more product they can make, the faster, the more money they can make, and it's all about the money. Absorption involves like penetration of that reaction on the catalyst, so it actually absorbs it. But usually we're doing adsorb, not absorb. Okay. Here's an example of hydrogen and carbon going through the catalyst, so then they're able to react. It's just like ethylene, which is C2, C double bonded 2 is what it is. Yeah, C double bonded 2. And then from that, they often can make things like ethylene glycol, which is used in antifreeze. Here's the difference between the catalyzed and the uncatalyzed reaction. They're using chlorine here, of course. And notice it's Cl. Oh, let me ask y'all that. Which one is the catalyst? Which ones are the intermediates in the catalyzed reaction?
Cl intermediate.
What? Do what?
Cl and intermediate.
Cl is not an. Cl is the catalyst because it's appearing as a reactant and reappearing as a product. They still will cancel each other out and not appear in the rate law, but you start with it and you end with it, so it's still there because the catalyst is not used up in a reaction. Now, for the overall reaction, we're going to cancel them because they're on opposite sides. Okay, and then which one's the intermediates? ClO and O2. Yep. Okay. Is that bouncing or is it my imagination?
I can't tell.
The screen.
Back here.
It's not doing it as much. While I go, look, it looks like it's bouncing.
Yeah. If people like move it,
That did do it.
It bounces more if I just glance at it, and then when I stop and actually stare at it, it seems to stop.
I think
Yeah,
that's
look at
your
it from the
brain-
side.
I
Is it?
think it's your brain's perception of it.
I think you're having.
My brain is messed up, is what you're saying?
No, everyone. I see it too. It's just like, it's
Okay.
like, have you ever seen like those illusion things where you like stare at it really
Oh
hard
yeah, and
then
then you
look
get
out
the
and
thing.
off the side?
Or if you ever see, like, if someone's filming and there's a computer in the background, it's bouncing because your brain's faster than the camera. Some people's brains are faster than others. This is just showing you, for those of you that you are interested, that's what a catalytic converter looks like, and that's how I think almost all cars have a catalytic converter. That's how your car runs, able to process the fuel. How does the reaction mechanism for the catalyzed versus the uncatalyzed reaction? There you have EA with the catalyst and then without. And that one has got a multi-step process. That's why it's just one hump is enough, but that one is changing a lot. I don't like that one. In the end, okay, that finishes off our notes. So you have several packets to be working on.